All right, welcome everybody, day 29. So, we are gonna continue what we did the last episode, which is explaining how the Maya graph works. We're gonna get a little bit more practical with the application of what we've learned. And I mentioned it in the web post, like whenever I post videos, remember I also post on the website for Code of Rig. Link is down here. And the reason for that is not that I like to put up WordPress pages and stuff like that. It's that YouTube descriptions and stuff like that might go anytime. YouTube isn't like what I say on the actual stream is obviously not searchable, but web pages are, and I index them and tag them and all of that. So an example, I mentioned an Autodesk document that you should read, even if a lot of it might go over your head if you're not a developer. The link is going to be there. And occasionally we'll mention things like this stream is very chill. If you don't care for that kind of stuff, you might not want to waste your time. The document I did mention, which is going to be our basis for this episode, is using parallel Maya. And the 2018 one still seems to point to the 2017 one, but we're okay with that. 2016 and 2017 is where most of the stuff happened. So, the last time, previously on Code of Rig, we mentioned how the DG works and all of that does. Now, to get into parallel, it gets a little bit more complicated. And I don't think we can completely ignore some of the basics of how your CPU works and what multithreading and parallelism involved and all of that. If some of these goes over your head, don't worry. There's I kind of have to mention things that might only make sense much later to you in your learning. Don't feel stupid. Don't think that you can't follow and all of that. It's the idea of seeding knowledge. It's the idea of having something in the back of your head that you will eventually understand. On a similar note, I guess, but the other side of it is we are gonna approximate a lot and keep things very simple because knowledge of these kind of things tends to be very stepped. So, what do you need to know about your CPU? Because there's a lot of confusion about that. People say, why don't Autodesk or why doesn't our R&D department just make these multi-threaded so it's faster? Why don't they move these to the video card? Yada yada yada. And it's like some problems are pretty hard. Some problems are very, very hard to move around. So what you use nowadays, and we're gonna keep it very, very limited and simple, is a von Neumann architecture. And the basic idea of von Neumann is basically that you have a processing unit. In fact, it wasn't even called a CPU, it was called a processing unit or a logic unit. You have memory. I can do this. I believe in myself, I can do this. And the two basically talk to each other over a bus, which is not a vehicle for transportation of large amounts of people. It's actually a channel for things to communicate. That's about it. That's the idea of a Neumann architecture, and you might think it obvious and simplistic, but there were competing architectures, and there still are other separations. And the main differences were that the von Neumann architecture basically decided to have one block of memory for everything, one processing unit. There was no division for the code memory, so the instruction memory versus the data memory, because your program, your software actually lives in here somewhere. Maya is in here. I can do these as well, maybe. Maya is in here. There's a bunch of humanly unintelligible gibberish that the CPU understands, which are literally the instructions that it needs to run. There are addresses in memory that say, hey, the execution of the program is going down this thingy here. Read this instruction. This instruction is add, and it's got a couple arguments. Those two arguments are here and here in the memory. I would very much like you to do the deed and if possible, please then put it into this piece of memory so that it's accessible. The next piece of code comes in, the CPU reads it, knows that it's a divide, decides to go in there, and hopefully you get the idea. That's the basic idea. Code, instructions, the data that they require, the places that they write to, it's all one thing, and the CPU and the memory talk over a bus. That explodes into a million details. We're not going to care about it. Devices, interrupt versus polling, and so on. Now, what changed over the years is that eventually we couldn't get CPUs any faster. So we started getting more cores. And at the beginning, like, people were very confused about this, understandably, because multi-CPUs used to be a multi-socket thing many years before. And when they were saying, oh, you're getting multiple CPUs on one CPU, it got very confusing for the uninitiated. So when you hear multi-core and in your CPU you have 4 physical cores, they are literally, for the most part, complete CPUs that just happen to live very close to each other. Now, they talk to each other over an internal bus, which is considerably faster than the one that goes out to the memory. But the basic idea is the same. We're not going to go into too many details. There are things called caches, which are basically small bits of very, very, very fast memory inside each CPU. There are multiple levels of caches. There is... there is a higher level of cache again, which is the L3, which takes care of dealing with memory that is shared between multiple CPUs, and then eventually you go out to the main block of memory. We are gonna blatantly ignore one thing, which is the GPU, because that adds another layer of complications with readbacks and the such. We're gonna leave in CPU world for these, because that's what the control rig mostly gets to work with. So let's say that deformations happen on the GPU, you got everything working with the Maya GPU evaluator, your control rig is still in this space. Now, you might have heard about hyperthreading and you say, oh, you got 4 CPUs, but you got 8 threads. Now, your CPU internally, for quite a few years now, Intel calls them superscalar CPUs, so there is some internal parallelism. Your CPU can do several things at a time. That is where we stop. There's all kind of things like instruction pipelines, all sort of like higher level mechanisms to make it faster in certain situations. We don't care. When you hear 8 threads, because you hear about hyperthreading, it basically means that if there is a unit of work, actually let's go somewhere else. There is a unit of work, some description coming into the CPU. It might not use all of the CPU. In fact, it's almost guaranteed that it's only going to use a small part of your CPU, which is divided into a staggering number of different parts. What hyperthreading is that, you know, you might have another unit of work and you still have 3 cores, so it might just get dispatched to another core. And do I need to indicate these? Sure, let's do it. My daughter is being dramatic. Core 1 actually should be 0, and you know, you get 2, 3, and 4. Clockwise, it's bad. It should be counterclockwise, doesn't matter. Now, let's say that all of your CPUs have been pegged by various tasks, but they are not fully taken. Another task comes along, and maybe memory-wise, that is pretty close to this one task. So this is task A, this is task B, and we're gonna have C and D and whatever here. Some task F comes along, it seems to be geographically close in memory with what it requires to this one. The hyperthreading part is like, if this thing looks like it will fit on this part of the CPU, again, thinking model for things, so that you have some way to understand, think about the problem and understand it, then the CPU might be smart enough to go, hey, you know what, I can actually execute a second task on this CPU that doesn't have a lot to do with the one that it's chewing through. Maybe this is very lightweight and it's just arithmetics. It's using the floating point part. And this looks like it's entirely integer arithmetics. I'm not really doing much with that. I have a couple pipes still open. This is what might happen. Hyperthreading is basically that. So when you look at your CPU, I'm on a Haswell 4 cores. Let's have a quick peek at that. I don't see it here, do I? Anyway, we can still show something. When you open your task manager and you see sockets, is the number of physical packages, cores or the number of dies on your CPU, and then you get logical processors. That's how many different logical units you can basically deal with. Hopefully that still makes sense. There is a lot about contention and cache coherence and all of that makes a big difference if you get into the details, but you have no business with that once you're in Maya anyway, because Maya does the hard work. Is this making sense up to here? I hope so, because I reckon that this is more or less all you need to know about how the CPU works to deal with these things. So on the other side of the fence, you have the operating system. So the operating system is actually the thing that manages all of these for you. So there is an abstraction for these things where the operating system takes the memory, makes and serves pages of memory for applications to use. So you never really see the raw identity of this stuff, unless you're writing for embedded or you're writing in the kernel space, so very close to the OS. You're writing drivers or whatever. You always see what the operating system shows you about those things. So when you open Maya, what happens is that your OS opens a process. The process gets to fish some pages from the memory. So you're in control, you're the programmer, you create an application, you go, hey, right out of the gate, give me a memory arena of 4 GB, because that's, you're developing a game where constant allocation is convenient. And that is basically what you are gonna be managing as a developer. Now, when you want to use multiple CPUs, you don't go to the CPU and say, hey, get me core A, get me core B, I want to write in cache. No, you don't do any of that. The CPU through the OS has a lot of control about that. In fact, the operating system hardly has any dealings with the cache itself. The CPU is a massive internal piece of software in its own right. And the operating system deals with that stuff. Now, what you do is you're in a process and you say, hey, I would actually like to do something, and I know I can do it in 2 stages because I have 2 legs, and I know, so we're in some Maya space, I know that they're independent of each other. So if I have my God node here and the 2 legs depend on it, then I know that they don't require each other to work. So what you do is you can ask a process for threads. And the process spawns, well, I was about to write in Linux. Let's not write in Linux, let's write in abstract. It will, on your request as a programmer, it will pop a couple threads. There's a cost to doing this, so you can't just, and there's not as many threads as you have CPUs. Applications open thousands to hundreds to thousands of threads. And you go, okay, you know what? I have 4 cores. There's no point in doing the leg until I have the God node. So with thread 0, I am going to process the God node. That creates this output that is useful and comfortably close to the leg. So I'm going to do the leg on that thread. This stuff, in here, it was done in thread 0. It needs to go in thread 1 for that thread to be useful, remember when we're showing, hey, maybe the node copies some graphs. It's pretty common, and again, a lot of this is actually going to be done by the CPU or libraries. You will, even if you're a developer, you will hardly ever deal with this level of granularity. We're going to copy a bunch of stuff for thread 1 to use, and then that thread can go pick it up from another CPU and do that. Still making sense, I hope. So this is what is basically going on. Now, this is a very simplistic view, but it's actually a pretty valid way to look at the problem and how the work you do maps to the actual CPU, minus a gazillion kilograms of details. Oof. So chat, give me a hand. Let me know how things go, and let us have a look at what is going on with Maya. So here's our graph, and if you press play, I think we have some animation for the foot roll. It's in guide mode and whatever, so stuff is happening. And this is what we're talking about the other day, which is, okay, no, need to remap brain. New to me, but kind of makes sense. Yeah, if this sounds, if you don't get all of it, if it sounds scary, if you don't understand it, don't worry. We're seeding here. It's the fact that you know it exists is enough. You don't need to know the details. It's just a model for you to understand what is the connection between your CPU's workload and what you're doing here. Now, in our very, very, very primitive model, when we explained things the last episode, we were saying, look, there's a good example, which is you have some manipulation loop, and that was the DG case. You have some manipulation loop that dirties something up here. Sorry for that, but super scratchy throat this morning. And something needs to be drawn on this end. We will go backwards, find everything that we suspect, this thing here, this transform owns a shape. So this transform, very simplistically can say, hey, on this other end of things, you have a list of stuff to do. Is this shape in it? If it is, then that shape is going to go, oh, I am dirty, I feel dirty, I need to receive further information. And it walks back through the graph until it finds all parameters that have changed and then knows what to do with them. And then, we'll build an evaluation, a subgraph, I guess, for the evaluation. And if you're in DG, it might be the dirty plugs and all of that. It's dirty plugs basically. Or it might be some other mechanism that gets staged for computation. It becomes numbers. It goes back to everything else is drawn, and you go, good, I'm done. So there's this viewport loop where you're constantly catching up to the manipulation. And if you want to see a funny thing about this, I did an intro video to, I don't remember which stream it was, but it was basically explaining constraints and cycles and how the aim constraint is cyclic and what the effects are. And I show not really a bug, and I was showing what is like undesirable behavior where you go like, this might look like a bug to you. It's actually an unintended consequence of the fact that you are in a weird space here. So yeah, that's key. And you say it's where you manipulate something and it jumps all over the place. That might exemplify what I'm saying even further. Now, here's how it works for parallel. Now, when you're manipulating, it becomes pretty obvious. The internal mechanisms in Maya are likely to be a lot more complex, but there are some pretty obvious simple thoughts you can entertain about it, which is, if I'm moving something, and this is like it or not like it, doesn't really matter. The decision that Maya had time ago to have shapes as a separate item from the transforms has not been a stupid one. Now, what is happening here is you're transforming this object. It has a shape underneath. So if there's, the whole viewport thing we're talking about, it's pretty easy to inform the beginning of the graph of what is going on. Now, you have a ton of stuff, however, that doesn't depend on that. So the DG was very strongly, it was very capable of being strongly, like, tightly coupled with what was going on in the viewport, which was why hiding something will, as a side effect, optimize some of the graph away. When you work in parallel, things get very, very different. So if parallel loves static data, so and you'll find mentions of that, a lot of them, in this document. And the main thing is, if you want something to work, and that is why when I start working on a rig, right away I put a couple function curves in there. You really want function curves in there. So let's say that we use these two items to do what? Oh, there's spinning going on. So let's try again. Let's say that we use one, which should be already animated. Yep, it has a bunch of function curves. And two, which is not animated, and we are gonna animate that TD animation, but we don't care. So when you scrub the timeline, for the record, it's the same thing as if you were playing. It will work in parallel. So why are function curves good for parallel evaluation? Well, it's pretty simple. Despite the fact that you might think of these as animated, it's actually static data. So when you're doing these, when you're going over time, by looking at these function curves, by looking at whether... Do I have anything in here? Okay. By going from frame to frame, if there is a change on anything, on any of these function curves, you know, on this kind of stretch, it is basically telling the graph, hey, something has changed for you. You need to do work. And everything that depends on you will need to do work. And we'll get into parallel now. Why is that important? So when you have something like this, in the DG mode we explain, if you're trying to do whatever amount of work you have to do, let's find something. Do I have that gun? No. Let me, sorry, I'm looking, trying to find something that makes sense here for these explanations. Sure. Like global ankle, we can do that. I want select downstream nodes. So I select these, and as it moves, I select downstream nodes. Everything that is being highlighted in here is everything this has an effect on. With some caveats about, you know, message attributes not really mattering and all of that. So you can see that it's a good chunk of work. Now, any of these nodes, depending on two other nodes, is basically a case where they are, in the general case, not specifically Maya, is a case where things need to be serialized. So I cannot, if I want to parallelize things, if I want things to become concurrent, so they happen at the same time, I cannot expect to run this node until I know what this node has produced and what this node has produced. And that is why things get sort of tricky. And I cannot run this node until those are done. So when you start looking at it that way, it can get pretty damn tricky to go like, okay, if everything depends on what was happening before, how do I schedule work so that it can actually happen in parallel? So we have talked briefly about threads, and threads are actually the operating system view of so it's very low level of how you deal with your CPU. There's another somewhat more recent, I guess, and very popular way to think of things. When you have libraries doing a lot, you don't access the operating system right away, you have libraries doing work for you. And to my knowledge, that's what Maya uses. Intel has a library called TBB, which is thread building blocks. And that is called a task-based system. So what happens is that instead of having threads and dealing with the low level of the CPU, and obviously these being Intel, they have a very good idea of what works and what doesn't, you build tasks. So you don't do this thing with the threads where you are, you know, saying, hey, this needs to occur before that, this needs to occur before that, and so on. What you do is slightly different, where you have a dependency graph. So you can go, I reckon we need another color for these. So you can go, hey, this is a task. I would like the God node to be evaluated. So this is my task 0. And this is a task. And I like my leg 1 to be evaluated. So I created a task for it. And this is another task. And so on. And you can imagine, you know, your rig, the way we've done components to fit neatly into these boxes. Then you have a dependency graph. And this is a game where we'll stop on the details. There are many, many ways to build a pool of things to execute. But you could say that this needs to happen before that, because you have a dependency graph and you can quite trivially say, you know, these things are dependent. And you could say, look, this is a weight, this has a weight of 0, and these have a weight of both of them 1. So what happens is that, or you could literally build a graph, a dependency graph of tasks. There's systems, primitives, whatever you want to call it, to do with that. And then it's up to the library to go like, hey, okay, this is one thread, and it's got to happen before those. Then this is another thread, and this is another thread. And the way it works is that these two, sorry, not another thread, another task, it's a separate computational unit. I can say that these two can use the same thread because they depend on each other, and they need to be scheduled first in this order. And this one, depending on that, will need to go second. Sorry, on the first thread, on the first core. And this can go on another one, but only when the life of this one has gone this far. So the library does this kind of thing for you. Now, hopefully you are still with me. The bit that regards Maya now, where that comes together, is, okay, so how are those things done in Maya? And again, we are shooting, actually, let's go full screen here. If I can. No? Whatever. Pregnant with anticipation, the silence is. So, we're somewhere here, and we have a look at these. What the DG gets us is basically these sort of relationships where you go, hey, this is roughly dependent on that, this is roughly dependent on that, there's no conflict between these. So then, and that's why Maya needs to do a DG pass first. Now, once that pass is done, what happens is that it can figure out that this is a task. Nothing depends on it. Only one thing depends. Sorry, it doesn't depend on anything. Nothing is upstream of it. Now this is another task. You know, it depends on one item. Several things depends on it. And then you get to here and you go, okay, as this is being walked, you can find a clear flow going that way. And based on the dependencies, this is getting, why can't I do straight lines today? Okay. And you go like, well, going by the dependencies, you know, you don't want to cross things sideways in an odd way. These look like three very separate things. And then this goes on. And again, you look at what is depending on it and all of that, and you go, okay, two things depend on these. So I want to be done with this unit of work before I go out, because, oh, I was trying to browse the graph here. Because several things depend on it, it's kind of risky to extend this further, because if I were to extend it all the way here, then something downstream of this one would require a previous state of this task. Not good. And again, fault model, not necessarily how the nitty-gritty details work. But then we move on, and you can look at this being another task because of the way this chain works. So if two things depend on something, you kind of want to stop the boundary of the task. But something depending on two items, that's a different deal. And this might be two, or it might be one. We'll get to it. Now, on a similar note, we have these, and these. And you can keep going on. Now, this depends on two. You hopefully start seeing what I am saying here. And let's say that we use our trusted. What do we use? Letters or numbers? Let's use letters. Chat, give me a sign of life. I need your help here. Are we still making sense? Let's go for it. Okay, mostly because it's readable. With you so far, still following. Cool. Now, the next thing we need to sort out is what order do these things need to happen in? If something is literally dependent on, something is not depending on anything, you can always schedule it, because you go like, okay, I can always run this unit of work. So F, like we're at, like while in our graph, because many things converge into the following block, might look like it's after this stuff. F can actually happen right away. There's nothing coming into it. Same for A. So we could go, okay, you know what? A and F can happen concurrently. B needs to follow A. Then you have this expansion where you go, well, all these three things need to wait on B, but they can kind of do their own thing. Now, as we go through here, there is a dependency between G and this stuff. So you go, okay, but G can still happen first. Now, H will depend on G, and I will depend on F and G. But I does not depend on H. So you can go from there and go, we were saying H definitely depends on G. I depends on G and F. Have we covered everything? Looks like it. Well, there's K, which depends on H and E. So let's do that. Now, if we look at it that way, hopefully it starts becoming a little bit clearer that there are many nodes in each of these units. Not many. I mean, we're looking at pretty small chunks, but these are not the Maya nodes any longer. But they are parallel units, so you can go, okay, you know what? These three, what am I doing here that you are not liking? Am I drawing in black? I'm probably drawing in black. Let's switch color again. So these are clearly 3 units of work. Now, the way these things depend on each other, we want I to wait for both of these. So as soon as these two can be done, I can schedule these to run. As soon as A is done, I can schedule B to run. As soon as G is done, I can schedule H to run. Then in here, so I have already sorted out a good chunk of work. And given what time you're waiting for and all of that, it looks like I'm using at least 3 cores here, because I can do all of this work somewhat independently. Now, moving on. C, D, and E only need B, K needs both of these. So, and hopefully this will actually help you make sense of when I was saying preloading, front-loading some of the work. So if we look at it this way, what you get is you have 3 here, you have 3 here, 3 here, and then at some point you are narrowing down to 1. This is your thread utilization. This is good space. If you add 4 threads in all of these, this is the amount of CPU you're wasting. So we're making pretty decent use. Chances are that we're using half or more of the CPU. Extend these to many threads, many nodes. You can see how these can get pretty complex, but this is the basic idea of how this stuff is sorted out. Now, if you remember, when I was talking about the leg global and front loading things, we want to make some sense of that. I was saying, look, if you solve these, if you really think about it, the leg itself does not need to have this stuff in it. The IK solution sure wants to know a couple things about it, but that's about it. If you don't split the leg global, then what you get is that the God node, primitive terms, but it's pretty functional. The God node needs to be done before the foot can be done. And if the foot is, in some condition before the IK can be done, maybe, if you don't split these because you're inside the same big leg, then the FK would also need to wait for maybe this to be done for some very minor dependency. And then you gotta blend the two, and you're praying that your graph sort of works out. And it doesn't seem to go quite that way. Again, these are sort of artificial constructs, but they are applicable. So this becomes pretty hard to schedule. But if you look at things a little bit more granularly, and your God node is actually made of 4 elements, actually, scrap that, ignore it. Let's not complicate things. So as soon as the God node is done with the chunk of nodes in its inheritance, so say up to here, let's go this way. So the God node is evaluating, this is time. As soon as it's done here, whatever this node that we're referencing for the distance is, I can start working on the foot. And I can start solving the foot roll. And the God node is going to take no time at all to run. So we're introducing time now. Whereas the foot roll is likely to be fairly expensive. Now, the earlier you can get out of a process, because Maya will build tasks based on bunches of nodes, not on our rather large components. The earlier you can get out of a process, the more chances for parallelism you have. Now, the more you divide, the more you also duplicate work. So because of the foot, we're computing the distance stuff more than once. But if you're in serial mode, computing the same thing more than once adds up. This is your time, and the less time you use is bad. The less time you use, the better. If you're in a serial mode and you computed the length twice for some reason, let's say you have the IK, then you do the length again, and then you do something with the foot, this is wasted time. But when you're in parallel mode, you are not thinking about a line of time and niftily arranging as many things as compactly as possible. You're now thinking about a surface problem where you want things to be packed in 2 dimensions as tightly as they can be. So while the foot roll is running, I can't really, while the foot roll is being computed, I can't really do the IK. I keep using the Alt and picking black color. So the IK, in simple terms, needs to depend on that. But the FK, however, if that foot is somewhere else, beside the fact it's also partially in parallel with the God node, can actually start right away. And maybe it has this much work to do. Now, the blend is likely going to be fully dependent on both. So the blend itself is going to be in here. But what has happened here, despite the fact that maybe that length, you know, we wasted this much time doing the length here, and I don't know, artificially speaking, you know, we've redone the length here, our whole time is that. So we come out ahead because had it been entirely serial and not parallelized like this, the God node would have been here, and then you would have had the foot roll, and then you would have had the IK, and then this FK, if it's not decoupled, despite the fact we're duplicating that effort, ends you there, and then you add the blend. So it's not that by doubling the number of thread we've doubled the performance, because you're gonna have bubbles in here, you're gonna have empty space, depending on the length of those tasks. When you look at it like this, it looks nifty and it looks like you're super parallel. The reality of things is that you're always gonna have bubbles when you're trying to split tasks so that they can be multi-threaded. But you are going to be coming out ahead. Now, the other thing is that within reason, the more you do these, the more likely you are to scale well with multiple cores. So when your hardware is upgraded, like for many years before I introduced parallel, unless you were working with some proprietary system, somebody would upgrade your CPU to something, from something that had 4 cores and was running at 4 gigahertz to something that has 12 cores and it running at 3.2 gigahertz. You have a new CPU and your rig is going slower because the overall computing power of the CPU has increased massively, but your base clock was literally in serial mode, all that mattered. Now you scale with cores to some extent. Okay. So that's the theory of it. That's how things kind of happen so that they can be packed and executed across multiple cores concurrently. Chat, you with me? Still here, cool. So we have mentioned the profiler and we're gonna open it for just a moment. Come on. I have it on a shortcut, and I don't remember the shortcut here at work. There you go. I did remember right where it was though. So we've shown this before. You start recording, you know, you get yourself a few frames or you play the animation, you stop recording, you get some view of what is going on with your frame. And this is the evaluation. Now when you have it in this mode, what you see here doesn't make a ton of sense to you because this is a very stack wind and unwind kind of thing. But the easiest view for people to get is probably the thread view. And CPU and thread view are not really equivalent, but for the time being, without going into too much detail, we'll get into profiling eventually. Let's say that we look at the thread view, and this is the amount of threads that your rig is using, and this is the work you're doing with it. And there's trailing stuff, you'll see viewport, this is usually viewport soothing, GPU override and queue, yeah, bounding box kernels. Let's ignore that, focus on these terracotta nodes, which is usually most of the work in your rig. And you can see what I was talking about, I guess, in here. I hope that you can. I mean, I hope that you can see that pattern, that it's starting to make some sense. Now, there's, I thought, what is it? Alt Shift? Yeah. So if you don't know it, I found out about this very late. Alt Shift is vertical zoom. The profiler is, it can be a little bit irritating to use UI-wise, but it's, it could use a coat of polish. But it's an invaluable tool if you're rigging and you're performance conscious. So at this point, hopefully you can see that this is something going on in our thread. Then there's a bubble because this stuff is waiting on something, another bubble, then some work happens, and so on and on. And it's very possible that you see those bubbles because something here maybe needed to happen before this task that was scheduled to run could get there. Now, you know, maybe this is delayed like that because it was waiting on something here. Again, fault model kind of thing. Don't take this super literally. And maybe this is the way things are going. Who knows? But you know, and I honestly I don't know what, you know, scheduling parameters they use, but you can sort of see the bubbles in there. And this is a profiler view, which, you know, isn't quite compacting things the way the timeline goes and all of that. But that is the pattern, right? That is what we're talking about. So maybe this is actually two tasks that can just run end to end, but as soon as one is done, you know, you can go out to that. Who knows? Like that's very far into the internals of Maya. So with that explained, the next thing that we have to figure out is why doesn't everything run in parallel? What runs in parallel? What kills performance? Again, we'll do more when it comes to profiling, but a few things are worth mentioning right away. So quick answer to a quick question. Manipulation is always serial. Yes and no. So the reason manipulation is serial is that as you're manipulating, it is you are altering a lot of stuff at once, and there's a viewport loop, and basically parallel mode isn't ideal. It could be, you could use the same EM build parallel graph, run it in EG and manipulate it that way, but there's a cost in starting EM and building that graph for EG and putting it on, and you don't want to constantly rebuild that graph. So Maya needs to find a safe moment to build that, and occasionally if you press play and you see a bit of lag, and if the rig is massive and convoluted, that lag can go up to, you know, noticeable, like half a second to a second. That's when Maya is doing its work and figuring out, okay, I'm gonna build this graph and then the AG can deal with it. So the timeline was a good place in the animation, in the application loop. The timeline playing was a good first point where to put that, but manipulation was better served by what am I doing here? Okay, manipulations seem to be better served by I have animation, okay, to be better served by just staying in the G, so that you don't constantly have to build that EM while you are only manipulating things and maybe changing the topology of the graph. There's this authoring stage versus this consuming stage. With that said, they introduced they introduced controls that you can flag, so you can basically say that something in the graph is a manipulation kind of control, and that will do a lot of work. It will inform the building of the EM a good deal, so that when you manipulate those objects specifically, you're not really authoring, you're more altering, and in that case you might get manipulation in parallel, if that makes sense. I've attempted to say that's 2017. And this is where you have tag as controller and parent controller, which is going to give you some functionality for, yeah, it's in green, so it's 2017, which is going to give you some functionality for peak walking. I'm not going to go much further in that, but yeah, it's a tricky thing that they're doing, being backward compatible and doing all of these. So they had to pick their fights, and the very first part was like, hey, let's address playback, and then they started getting more and more of these graph building and exceptions and graph information and stuff into other tools. And I think that TJ was showing, so it's now public news, they were showing that they're working on background caching in the current beta. It was live on Twitch, so there's no NDAs or pub confidentiality being broken here. Now, almost there. So here's an interesting thing, I guess, what's interesting to me. OCD is kicking in. Let's not make OCD kick in. We have said that we find these dependencies and we flag nodes to be sequential or concurrent. So two can run at the same time. Those are concurrent nodes. If they depend on each other, they are sequential nodes. Now, serial means that things have to happen in a series. Sequential, most of the time, is used equivalently to serial, which just means, look, it's a sequence of things, and something will tell you, look, sequential also means that there's a precise ordering. So if I'm saying an element is sequential to another, it means it's immediately following that. We don't care about that kind of semantics. Now, and these are sequential and so on and on. Now, here's where things get interesting. We have talked about all of these parallelism and how things can get scheduled and all of that. Now, let's go back to the microscopic for a moment on how Maya will build its own tasks. So, if we're here, you will believe that you could go 1 and 2 and then do that and then do that and so on. We say that. But Maya can't quite work in such a simple fashion, not for all nodes. So if you use Python, Python has one thing that's infamous called the GIL, the Global Interpreter Lock. Basically, every process, and that is one of the reasons why I do mention processes, you can have multiple Pythons running at the same time. C code can be concurrent, so if you use a library, whatever. Python itself can only run once per process. So when you start one Python process, which is your interpreter, that, unless it's deferring to C libraries, can only run on one CPU, on one thread at once. And that cannot be broken. That's the GIL. It's an implementation decision, a million reasons for it, it doesn't matter. Now, when Maya gives you its persistent interpreter with Python, it opens a Python process, and there's one of that. And opening multiple, you might think, oh, why don't they open 15 of those? And say, not a great idea. So you have one Python process in Maya. I don't know if you have multiple, but we don't care, even if you did. This is true when it comes to this evaluation, because there's not being able to know some stuff, and I'm quite positive that they only use one anyway. So if this node, and Maya cannot know because of the nature of Python and a number of other things, if this is a Python node, it needs from somewhere that is, I need to remember, like, I know you can do straight lines in whatever. Python has this completely serial, completely sequential kind of, acquisition of the GIL by, actually, this is the GIL line. Something like a script running acquires the GIL, runs, then gives back the GIL after its runtime, and then something else can acquire the GIL, runs, and, maybe has a couple steps, and gives back the GIL. So Python can only run one thing at once, and there's no real knowing without spending a lot of time trying to figure it out. Yes, Python nodes are bad. That's what I'm about to get to. Very bad. They're the worst thing you can do. There's no knowing whether it's doing things or not. So Maya has to be cautious. When it encounters a Python node, and this is something that we'll go back to the document in a moment, it can do nothing else but say, here at this point in time, remember how we were saying that our nodes get shuffled like this? If it encounters a Python node here and there were a million opportunities for concurrency, it does not matter. It has to collapse everything because it cannot risk the GIL being conflicted. If you have 48 threads, it doesn't matter. When it encounters a Python node, it has to pay the Python tax. All nodes have a tax. So there's always an initialization. That's why you don't divide things into a million nodes. There's some cost in spinning one up. there's a massive cost in spinning Python up. It has to let that Python node, however simple and optimized you might have had it internally, do its thing. And then it has, from there on, my daughter must be destroying something. And then it has, again, to re-spin up everything else it was doing. And because of the unknowability of these, which might be massively altering the DG, it's possible that you incur in a lot of verification tax here. Python nodes are really bad for that reason. Nothing will murder your performance like one of those. So instead of having this opportunity for parallelism here, what you have just done when you have a Python node is, this is basically, you know, this is fine, it'll run. This is fine, it'll run. It goes like, okay, this is a parallel task, I can deal with it. This is a parallel task, I can deal with it. And then it encounters that. So what it has to do is this stuff has to be scheduled so that there's no risk. So the reality of it is that the scheduling ends up, you know, this node, this node, this node, then the Python node, before it, and then maybe this node or whatever, before it finally gets to running that one and that one maybe in parallel. And then it can run that maybe on another thread. So you've just gone from free course blazing for a good amount of time to, and you know, and taking whatever time this would have been, it probably would have looked just about like that, for just one innocent Python node to taking time and a half, or possibly more, because this Python evaluation here, which I'm, you know, I don't know where I'm indicating it now, but I'm generously putting it on par with, you know, function curve evaluation and all of that. It's likely to expand. It's likely to be pretty big. Pressing image gets you line to, oh yeah, you like, oh, okay, not quite what I wanted, but that might be another button. I'll have to learn it. I used to know it, whatever. Thank you. Now, hopefully that's still making sense to you. Python nodes are bad, and that is what is called, so this is where we go back to the document. When you write a node, and Maya has its own node, so the Python node stuff is, you can think of it as a kind of node that can host the Python interpreter and deal with it and the negotiations and all of that. When you write nodes in C++, Python nodes are basically always one type of node, which is a Python evaluator. You get different types of nodes that you can flag. Now, these are the supported modes, which is, and there are constants that you pass, where you have k parallel, k serial, k globally serial, and all of that. I was hoping to find them for you. There you go. So you have scheduling types. When you create a node, you can schedule, you can inform the scheduler that does all of this partitioning and shuffling on whether your node is parallel, serial, globally serial, and untrusted. So untrusted nodes, and he'll tell you what they do, are deferred as much as possible. So if there is nothing left to evaluate that doesn't depend on that, then, you know, it'll do it. Now, I don't know if the Python node is globally serial or untrusted. The untrusted stuff you normally use for things that can self-cache, but it doesn't matter a whole lot. Well, it kind of does, but you would have to ask the Autodesk folks that, or I couldn't. Anyway, doesn't matter. So globally serial, so untrusted is really bad. Basically, Maya will try to do as much work as it's possible before. When he finds one, he'll do everything he can that he finds that can be done before it, and then go like, all right, I am now gonna do that untrusted node in a safe sandbox somewhere while everything else waits on it. Globally serial is, so no, Python is untrusted, I believe. It is safe to run this node with instances of other nodes, but only a single instance of this node should be run at a time. Now, which fundamentally, it's actually pretty simple, means, and this is male expressions, means that the Python thingy could be doing ungodly stuff everywhere, mel, and we do have one expression, and that is why I was saying, look, it's a bit of a myth that mel is slow. Mel is not slow. Let's make that clear. Unless you do stupid things with it. Well, not stupid really. There's all kind of cool hacks you could do with it, with mel expressions. So when we're here, what is actually happening with a mel expression? The Python one is untrusted. It finds it, it goes like, all right, gonna stop everything else because this is nuclear. When it gets to a mel expression or to a node that you have written, because maybe it has an internal cache, but it's an easily synchronized internal cache, you know, it could task things this way and go, okay, I have these. My draftsmanship is getting worse by the moment here, but I gotta go through the rest of these in the next few minutes. The Python node here, so actually, let's simplify this. The Python node here would, I'm lying again actually, this, let's say that this is actually a very long running chain. And maybe somewhere in another component, because here I'm showing things this way, but if we had another leg, you know, you would have the equivalent one. Chances are you would have the equivalent one running. And if you had the arms, you know, you would have another one running here. Hopefully this still reads. And another one here. Python would have basically have stopped the whole machine. Now, when this is encountered, which is an expression, if the other leg was running, and it has, you know, some sub-blocks like that, and the other leg was running, and it also had an expression, it does need to partition that. So what you get is that kind of effect where the expression needs to be partitioned out of this sequence. So your time occupancy is this. If you only have one and no other expressions run in parallel, it's pretty unobtrusive. If there is another node of the same type running at the same time, exactly at the same time, these have to be scheduled offset. So it will basically go, okay, I can only run these. This is like a shared timeline. I can only run one of these at the same time. So this is our leg left in example. And our leg right kind of runs its own thing, finds an expression, another one is being evaluated. There's only one thread at any given time that can evaluate those expressions. It has to wait and go off to here. Chat, is this making sense? So that's globally serial. And that's why if you have a ton of expressions, and this is because there's one mail interpreter, but that mail interpreter isn't too bad and it's knowable because Maya implements it. And as you create stuff inside that expression, it will create ports for you and all of that. So this is globally serial. Python is untrusted. It will collapse your entire tree to one thread until it's done, and then it'll do the rest. Mail expressions or nodes that you write that you flag as globally serial work like this. Unless you're doing something ungodly with it, but we will get to it. So okay, sorry, I was reading things for a moment. The other type again is serial. It's pretty rare, but so whereas in this case we only have one thread that can do mail, serial I can't really say can't think if anything I'm using these days that is serial, but let's cover it anyway. Now we have said that globally serial means at any given time only one thread can run that. Serial, simple serial, which sounds like breakfast, is actually even a little bit more forgiving than that. If I have one evaluation chain, so one of those islands that we've identified, which might thread further for the record, if within that chain there are two nodes that are flagged as serial, now if in theory that chain of events could have done something like, let's make our serial ones blue, edit everything being green, maybe these things could have been done in parallel because they both affect this item had they not been serial. And then these things, you know, these maybe has a chance to be parallel to that. And then all three of them in that chain of evaluation could have talked to that. So on the small task threading level, Maya could have gone, you know, 1 core, 3 cores, 1 core. If they're in the same chain of evaluation, remember when I was saying, you know, maybe internally it duplicates node into virtual nodes. That's kind of what might be going on here. It has to behave differently, and it has to serialize those two. So what you will get is, in fact, gonna be this. And you can see, you know, over the line of time, this is a little bit more expensive. Now, if the other leg was in a similar situation, if this was male, it would have been offset even more. They would all have to be in a sequence. But if the other leg has the same nodes, but they're not in the same chain of evaluation, then you will get the same shape for the subgraph in the other one. This is what serial nodes do. So bad-ish, but sometimes needed, especially when you have some caching mechanism going on, not competing with each other so long as they're in separate islands. And then lastly, you have parallel, which means you good. Parallel means every other node that we talked about. So I'm trying to think about what is next. I think that's more or less it. Does this make sense? Do you now sort of understand what is going on and how the parallel graph works and why, you know, some meets shouldn't exist? And like, oh, expressions are slow, and it's no, they're actually pretty fast. I think on the profiler, do I have the profiler up? No, I don't believe I do. On the profiler, I'm tempted to say this is gonna be, depending on your clock, I just downclocked my PC, but it'd be 40 to 60 micros, I reckon, something like that. So can I zoom in on you? Do I have synchronicity? No, but I know I must learn C++ now. If you want custom nodes and you want things to be fast, break them out into expressions if you have a small enough rig, or learn C++. There is no way around it. I am sorry. It is sad news, but Python is just bad for this stuff. I like the language, I like its history, I think Guido is an absolute legend, but it is not a good language for performance. So, alright, here you go. The average run of this expression is 43 microseconds. They are not slow. Do your own Python node, put it in there, see how long it takes to do the same thing. Literally, do what I've done here and put it in there. Now, the caveat for the globally serial nodes, expressions are important until you can have your own library of optimized C++ nodes, or you can write so fluently that you don't need them. Expressions basically evaluate the whole script. So if you have an expression that is very simple, the way we do here, and very clear, do I need, yeah. So if you have an expression that very clearly has a bunch of inputs and a bunch of outputs, and all it does is operate on those and nothing else. So in here, in the body of my expressions, I never, ever look at anything that is not coming from here. So I don't do, oh, because you can do some crazy stuff inside. You can do, oh, ls, find me the node that has this. So that people were doing expressions that were somewhere in the graph and would look up somewhere completely different in the graph that had already been evaluated because they could rely on the sequentiality of all of these, making a decision based on that. So you could do some super fancy animation friendly controls where things will move and so on. if you do that, then this node has just become uncertain about its position in the graph, because from being here and knowing exactly what its neighborhood is, now it knows it's relying, it might or it might not, because if you're doing NLS and processing the string and fetching the other node, it has to be evaluated in full just to know where it sits in the graph. And if even worse, from it, you are sure writing out to the plugs here, but you also have something sneaky where again you build another node or you inspect these plugs, and this is what I was talking about with the old set dependence dirty tricks. Maybe the scripting here squirrels along the graph and finds this node and does something a little bit tricky on another plug here, and it can be figured out from its ports, then that has just become untrusted. This node is doing things that cannot be trusted to be where this node is in the topology of the evaluation, the topology of your graph as you see it in nodes, and as the EG can have it resolved by the EM, has just gone completely pear-shaped. You are out of luck. So Maya will basically flag it as globally as untrusted. Exactly the mechanics of how it's down to the nitty-gritty, again, I don't know. You would have to ask my engineer. I am not privy to their to the internals of their code base. But most likely what is happening is that as you run a graph, as you run the timeline many times, as you evaluate things many times, internally they probably flag, like they probably evaluate it as untrusted the first time. They look at what effects it has, or maybe they run the script sandbox in a duplicate node. They look at the chain of consequences. If it's found to be worth it, if it's found to be a good node that only has an effect on its immediate neighborhood and is only affected by its immediate neighborhood, then it's promoted to become globally serial. And the fact that it's globally serial is that because there's only one mail interpreter. And if they actually made the mail interpreter something a la Lua, where you could spawn off like very small, very fast derived interpreters, then you will probably have the ability to have multiple mail nodes as serial, I will guess, in that case, or even parallel. I don't know if I covered everything I wanted to cover or everything that you need covered, but I've definitely run out of time. I hope this was useful. I think this is stuff that people should know if you want to rig fast rigs. You gotta understand this. And you might struggle for a few days, but you gotta have this in the back of your mind. You gotta be aware of what is going on to some extent. You gotta profile, and we'll show that at some other time. But you have to have at least this basic level of knowledge of the various types of nodes that exist. It gets a little bit trickier when you get to GPU evaluation, which is a huge boost on the information, but we're focusing on control rigs for now, and our skinning will be a triviality. Questions? You got very little time to ask them, so pile them up now. So how Maya build EG graph, what rules are, and what events will trigger EG invalidate and what events not? That's a pretty good question. Document, I think, the document I've been showing and linking so many times has a lot of information about it. Building the EG graph is done by the evaluation manager, the EM. So the EG graph is already built, and then when people say EG, or when the document specifies, let's say is EG, the graph is already there and it gets evaluated. The EM uses a DG pass, so the serial one, figures out the islands and the dependencies and stuff like that. Basically, it is a pretty good question, so I should answer it. Basically, the DG is run over this coarse graph that we had. It's the one that figures out the dependencies and puts them, in some order. Then that output from the DG is somehow parsed by the EM, which is the evaluation manager. I will refer you to the end of the previous episode for that. I show some of the, the candidates for choices they could have made. It maybe duplicates nodes, it might be doing some other tricks or whatever. But the EM builds this alternative graph, which is much simpler in terms of like what the graph itself describes, and the rules are much more constrictive, but chances are it has many more nodes. And then the EG receives that. Now, the details of how these days, how optimize the building of that, like what triggers the EM, I honestly don't know all the cases. Definitely if you reconnected a few graphs, so if you change connections, and I don't know how they detect it. I don't know if they have a hash table of all the connections and they diff the hashes or whatever. But if you reconnect a bunch of stuff and then you play the timeline, it will definitely need to do a good chunk of the EM work, if not all of it. Now, whether they have some partial islands and the EM figures out that, in example, you know all of these is still valid and you just invalidated these and does partial rebuilds, I don't know. I'm inclined to say they don't. It's maybe they're looking to do it. Changing the topology of the graph will basically do it. Actually, that's a good question for another reason. Something that you should know is that, and that is, sorry, all of this talk, and say, you need the function curves to provide static information, as much of it as possible, upstream of the execution about what needs dirtying. If you have no function curves, your rig is likely to not, it's got better with the versions as they find bugs and fix them, or undesired behavior. If you have no function curves, chances are your rig is going to be parallelized terribly. And there used to be this other myth where people were saying, oh, don't key everything and don't do this, don't do that. Sure, don't key everything. If you have a rig with 20,000 attributes and all the time all of them are keyed with flat curves, that's a waste of time. But if most of your components have a handful of function curves poking at something like the animated control parameters and the key manipulators at the edges of it, that will get you very often a faster rig evaluation, and it will help the DEM a good deal, in my experience. The other thing you should know, and I've seen people trying to be smart with it and getting bitten in the ass, nodes have a frozen attribute. Now, I don't even remember where it is. There you go. So every node in Maya that I know of, I don't know if it's an extension attribute for every possible DG node, but when you click frozen, it doesn't sing let it go. It actually basically says this node does not get scheduled into the EM anymore. So if you want to disable part of your graph, like if you want, you have two alternatives for the leg FKIK, and you want to bring in both, but you want one of them not to evaluate at all, if you select a bunch of nodes and all of them get frozen, it's like, there's gonna be jokes about this crap at some point. And if all of them get frozen, they will not be scheduled for evaluation. Now, I'm not saying they won't be evaluated. I'm literally saying they will not be scheduled for evaluation, because it's an important difference. This is not a dynamic attribute. If you ever connect it to anything else in your rig, make that a non-animatable static attribute. This changes the EM. This basically goes, hey, the work you've done for the EG, it's now, if this changes, it's now invalid, because I've actually decided I don't want to evaluate all these nodes. So if you have an animatable FKIK blend, you do not want to control these, because you can't change. If you change it during the playback, there are two things that could happen. One, it somehow gets tracked and your entire the EM has to run and the entire EG has to be rebuilt while you're playing, and your playback will always stutter every time you hit that change. More likely, it will just get ignored. So you will have, you start with FK, sets frozen on a bunch of IK nodes, it starts evaluating, it does things. You get to the switch and the graph didn't know to schedule any of those other nodes. Changing visibility will trigger EG invalidation. Visibility switching your rig will trigger invalidation. gets a little bit trickier again. So there's another thing that we have not talked about and then we'll not talk about right now, which is custom evaluators. The long story short is that you can build a custom evaluator. It has a rule, like it could be, you know, every node of type geometry, when the EM runs it, finds something that matches that rule, it dispatches the graph, figuring out the graph to your own evaluator that will actually do some of the work, or actually it will be responsible to tell the general engine how, in what order these things, all these nodes need to be evaluated. So you can do some very interesting things, but you're getting into pretty intense territory. Now, the visibility having an effect on stuff was an artifact of the DG. So if you're using 2016 or 2016.5, hiding a mesh that's deformed does absolutely nothing to spare you computation. It will still evaluate. You don't want it to happen, you have to use the frozen attribute. Now, as of 2017, I believe, and I would have to check, but I'm quite positive, there's this thing called Invisibility Evaluator, where they built an evaluator probably with the same API you have access to, or used it as an exercise to extend that API, that when it encounters a mesh and that mesh is invisible, it will do its damnedest to actually try and sort out the graph so that you don't waste resources. Now, there's no relationship whatsoever that is direct between something like the EG and the visibility of an object. It's an attribute like any other. But because it's such an important thing in people's minds, they don't think in the super general case they had to deal with it especially, and that's what the custom evaluator does. Custom evaluator can trigger invalidation. I'm not sure what you mean, but what about callbacks? Callbacks don't get called when you, well, most callbacks don't get called when you play. Callbacks are called by dynamic attribute changes and stuff like that. So if you're in manipulation mode, there are some callbacks that regard time and some callbacks that regard just in playback and stuff like that. Slightly different deal. All right, I'm gonna call it. It's pretty late. I gotta go. Callbacks will work. Callbacks don't have an effect of any kind. Like the callbacks as we have shown and the ones we've shown have zero effect on the graph once you play. How you trigger invalidation. I don't know if I use the word invalidation in a way that's confusing or you have something specific in mind. If you want to manually invalidate things, there's a bunch of tools, but we'll have to get into that later. You're racing ahead, and I suspect you actually have done your homework on a bunch of this stuff from other chats. All right. Much like the last one, this took longer than I thought. But thanks everybody for watching, and we will resume some noddling, but interesting stuff like symmetry and finish the de-guiding and all of that in the next few days. If you're following this, if you're bang on, and when I actually publish these, I might take next week off because I got a lot of stuff to do and I need a few days off from these while I prepare stuff for Patreon. If you're looking at these deferred, you will probably find everything in a sequence and you'll be fine. And once we actually have our thing, we'll quickly bind it to some geo. Don't plan to take any time for that. We're not doing skinning this season, and then we will move on to profiling. Maybe a little bit of optimization, though I kind of went already somewhat overboard with these, so there's not going to be great punchlines. You already know, don't do Python, use expressions sparingly, and don't do unholy things to the graph when you use them. Thank you very much for watching, and have a good day, everybody.